In this video, we're going to explain how floating point numbers are multiplied. We'll be focusing on normalized floats. Denormalized floats are handled similarly. Infinities and nands are handled specially. We'll assume that you're already somewhat familiar with normalized floating point numbers and their representations. We have a separate video on that topic, and we'll review it here only to the extent necessary to make our current topic intelligible. For this video, we'll be assuming 32-bit floats, but everything we say can be applied with some minor modifications to 64-bit doubles. Recall that floating point numbers are effectively a variant of binary scientific notation, that is, numbers of the standard form shown here. There's a sign, plus or minus, and a real number constant c in a specific format, times some integral power of 2. For normalized numbers, c always has a single 1 to the left of the binary point. In floating point format, numbers are stored in 3 fields: sign, exponent, and constant. The constant field is sometimes called the frac, mantissa, or significand. For 32-bit floats, we allocate 1 bit for the sign, 8 bits for the exponent, and the remaining 23 bits for the constant. Recall that for normalized numbers, the exponent is stored in biased form, meaning that the range of possible exponents, minus 126 to 127, is shifted in the positive direction by adding a constant of 127. This ensures that the value recorded in the exponent field will always be positive. To recover the actual exponent, we just subtract the bias of 127. Understanding multiplication for floats really is easiest if you think of them as just an alternative format for scientific notation. So let's consider how one multiplies numbers in scientific notation. We'll start with decimal, since it's most familiar. Suppose we want to multiply the two numbers shown here in scientific notation. That is, we want to compute this product. Since we're multiplying two positive numbers, the result is positive. In general, computing the sign of the result is easy. Using the commutative and associative laws for multiplication, we can reorder the terms to group the significands and the powers of 10. Multiplying these out gives what's shown here. Recall that multiplying powers of the same base involves adding the exponents. We're almost done. Our result is correct, but it's not in appropriate format for scientific notation, with exactly 1 digit to the left of the decimal point. So we move our decimal point 1 place to the left and compensate by increasing the exponent by 1. Now let's perform a similar computation in binary. Imagine we're multiplying the following binary numbers in binary scientific notation. First, we note that the result again will be positive, since we're multiplying two positive numbers. As in the decimal case, we group the mantissas and the powers of 2, which gives us this form. Multiplying this out gives this result. This answer is correct, but again it's not in the right format. We want to have a single 1 to the left of the binary point. So we adjust the mantissa by moving the binary point 1 place to the left and compensate by raising the exponent by 1. That result is shown here. Finally, this result is easily converted into floating point format. So far, we've explained multiplication of floating point numbers by doing the multiplication in the equivalent scientific notation. An obvious question is, why not just do the multiplication directly using the float notation? That's certainly what the computer does. Let's think about how that would work. Let's look at our two binary multiplicands again. In float notation, these are as shown here. To multiply these together, we'd perform the following steps. First, the sign is computed from the signs of the multiplicands. In this case, it's 0 for a positive result. Second, we'd compute the product of the mantissas, remembering that each one has an implied 1 in front of the binary point. Third, we'd compute the exponent of the product by adding the exponents. And finally, if the result is not an appropriate format, we'd have to adjust the exponent and mantissa to put it into appropriate form. Sounds straightforward, but there are some significant complications that make a floating point multiplier a pretty complex piece of circuitry. For one thing, each mantissa is stored with 24 bits of precision, but the product of two 24-bit numbers may require 48 bits to store. The hardware must compute the exact answer and round to 24 bits using the designated rounding mode. Second, both exponents are stored in biased form. Adding the two values stored in the exponent fields would yield exponent 1 plus exponent 2 plus 2 times the bias. That means that we need to subtract away one copy of the bias to obtain the representation of the product's exponent. We'd also have to worry whether the resulting exponent is representable in 8 bits and what to do if it's not. For example, we might return a positive or negative infinity. Finally, the product may not be in the right form, that is, with exactly 1, 1 to the left of the binary point. In that case, the result has to be adjusted, affecting both the exponent and mantissa fields. That has to be done after rounding the mantissa, since rounding can also yield an improper format. Sounds pretty complicated, doesn't it? And we've been looking at the easy case, multiplication of two normalized floats. There are additional complications if one or both of the multiplicands is a denormalized number or special value, or if the result is too large to store. The hardware must deal with these corner cases also. It's certainly possible to do all this. Computers do it flawlessly. But most humans aren't very good at it. So when multiplying two floating point numbers, it's typically easier for us mere humans to extract the numbers into scientific notation, perform the multiplication there, and then put the result back into float format. This requires some care, but it's a lot easier than trying to mimic the hardware. Today, hardware manufacturers typically employ formal methods to prove the correctness of their floating point algorithms and hardware. These are very subtle, and it's hard to ensure that they are correct through testing alone.